atoms, electrons exist in well-defined energy levels or shells in which they have a certain amount of energy. These energy levels are represented by a band. The valence band is the highest energy band which is occupied by electrons and is usually partially or fully filled. Above this band is the conduction band. Electrons in this conduction band can flow easily when an electric current is applied. These energy bands are separated by forbidden energy zones where electrons cannot exist. A material's electrical conductivity depends on how large the gap is. Electrical properties vary between different substances and can be categorized into three classes: conductors, insulators, and semiconductors. In conductors, free electrons are able to move easily when an electric field is applied. This is because their bonding electrons are held so loosely that when a small amount of energy is applied, the electrons are free to break their bonds and flow through the material. There is also no forbidding zone for most conductors, allowing the electrons to flow easily between the materials when an electric field is applied. As a result, conductors have very low resistance. However, this resistance can increase with temperature as the vibrations of the ions about the equilibrium position increases, which impacts the straight movement of the electrons. In insulators, energy gap between the valence band and the conduction band is too large for an electron to jump the gap to the conduction band. Diamonds are good insulators because carbon holds onto those electrons so tightly. Generally, a diamond would burn before you could force an electron current through it. It is very difficult for electrons to obtain sufficient energy to jump over this forbidden energy zone and enter the conduction band. Thus, there are no free charge carriers to facilitate current flow. Several solids have properties in between both conductors and insulators. These are called semi-metals or semiconductors. They are more electrically conductive than insulators, but less electrically conductive than conductors. This is because they have smaller forbidden energy zones than insulators, but larger than conductors' ones. Their electrical resistance decreases with increasing temperature, as the electrons gain enough energy to jump the gap. At low temperatures, the valence band is completely occupied and the conduction band is empty, so conductivity is low and resistance is high. At high temperatures, oscillations of the ladders provide electrons with enough energy to jump across the energy gap, increasing the number of charge carriers in the conduction band. Semiconductor materials include germanium or silicon. Both are group 4 elements. Silicon is more used than germanium as it is more abundant and forms an insulating oxide layer when heated to high temperatures, which is critical for integrated circuits. Silicon is a semiconductor example that we will use today. Silicon has 14 atoms and 14 electrons. It has 2 electrons in its first shell, 8 in its second shell, and 4 in its valence shell. Fun fact, silicon is a hard and brittle crystalline solid with a blue-grey metallic luster. It is a tetravalent metalloid and semiconductor. It is a member of group 14 in the periodic table, along with carbon above it and germanium, tin, and lead below. As the temperature of a pure semiconductor rises, some electrons gain sufficient energy to escape their bond. In doing so, they leave a hole behind. The electron and the hole become a pair. As the hole is created, an electron moves to take its place, creating a hole in its own place. Conduction occurs by the holes in the free electrons moving along. Silicon, in its pure state, is a medium conductor. Doping can significantly increase conductivity. Doping occurs when a group 3 or group 5 atom replaces some of the atoms of the element being doped. Doping creates a hole or provides an extra electron. As before, with the electron-hole pairs, conduction is created. There are 2 types of doped semiconductors, N-type and P-type. P-type semiconductors are doped with group 3 elements, such as boron or gallium, which contain 3 electrons in their valence shell. As the electrons jump to the conduction band, they leave holes in the valence band. These holes move through the crystal structure and act as positive carriers. In P-type semiconductors, there is an energy level at the base of the forbidden gap. This dopant level is called the acceptor level, as it accepts electrons from the valence band. These electrons move from the valence band to the acceptor level, leaving a hole behind. Neighbouring electrons move to fill the hole. This causes the hole to move in the opposite direction in the valence band, creating a current. N-type semiconductors are doped with group 5 elements, which have 5 electrons in their valence shell. This means there is an extra electron donated. In N-type semiconductors, there is a dopant level called the donor level. The electrons move easily from this level to the conduction band, leaving a hole. Electrons to the valence band move to fill this hole, creating an electric current when an electric field is applied. Negative electrons are the charge carriers in this case, and with P-type semiconductors, the holes are the charge carriers. Well, semiconductors are very useful. But so, who invented them, or created them, or discovered them? Michael Faraday was the first person to observe a semiconductor effect in 1833. Faraday observed that the electrical resistance of silver sulfide decreased with temperature. In 1874, Carl Braun discovered and documented the first semiconductor diode effect. Braun observed that current flows freely in only one direction at the contact between the metal point and the galena crystal. In 1901, the very first semiconductor device was patented, called cat's whiskers. This device was invented by Jagadish Chandra Bose. Cat whiskers was a point-contact semiconductor rectifier used for detecting radio waves. A transistor is a device composed of semiconductor material. John Bardeen, Walter Brattain, and William Shockley all co-invented the transistor in 1947 at Bell Labs. There is new research developed every single day, and it can be hard to keep up with all the developments happening in the scientific community. UCLA scientists have developed a new process for assembling semiconductor devices, which could lead to more efficient transistors. Their method joins a semiconductor layer and a metal electrode layer without the atomic level defects that typically occur when other processes are used to build semiconductor-based devices. Even though these defects are minuscule, they can trap electrons traveling between the semiconductor and the adjacent metal electrodes, making the device less efficient than it could be. The electrodes in semiconductor-based devices are what enable electrons to travel to and from the semiconductor. The electrons can carry computing information or energy to power a device. The UCLA method prevents the defects from forming by joining a thin sheet of metal atop the semiconductor layer through a simple lamination process. And instead of using chemical bonds to hold the two components together, the new procedure uses van der Waals forces, weak electrostatic connections that are activated when atoms are very close to each other, to keep the molecules attached to each other. Van der Waals forces are weaker than chemical bonds, but they're strong enough to hold the materials together because of how thin they are. Each layer is around 10 nanometers thick or less. The research is also the first work to validate a scientific theory that originated in the 1930s. Because of those tiny defects that have always occurred during manufacturing, semiconductor devices have always needed more electrons, more energy than a theoretical minimum. More efficient semiconductor devices will result in more efficient and quicker computing and will eventually revolutionize how quickly we get our information in the modern world.